welcome to the AI campus. It's great that so many of you made it here today. Very glad to have Adrian Sieler here today from TU Berlin and Science of Intelligence to talk a little bit about robotics and AI. The robotics field is not really represented here at the AI campus, so I felt like it would be a good idea to introduce some of these topics here in this format. And of course, the AI campus is a connection space for artificial intelligence and companies around this domain. So we have around 60 companies here on the campus that work all with artificial intelligence, and it's just a very nice opportunity for everyone to connect here and to engage in talks and the coffee machine. So yeah, we are very excited to host you today. Our company is called Merantix Momentum. We are based at this campus and have basically a consultancy business that helps clients accelerate the adoption of machine learning in their use case. And we also have a research department in which I work, and the research department basically also hosts you tonight in this paper reading group. And yeah, on to tonight's talk a little bit. I'm very excited to announce Adrian. He is a PhD student in the robotics and biology lab at the TU Berlin, sorry. This is, maybe also a little bit about my background. I have done my master's at TU Munich, which is why I just confused this. I have written my master thesis on a very similar topic on reinforcement learning and AI in robotics. And there were some loose connections, I would say, to your research group. And then I got introduced to you. So very excited to have you here tonight. And yeah, please just ask questions whenever you have them. We can forward the mic to you. Please ask questions through the mic so the online crowd can hear you guys. And I'll also monitor the chat online. So yeah, feel free to drop your questions in there as well. And without further ado, I'd like to hand it over to you. Thank you so much.
Thank you very much, Alex. So I also did my master's at the TU Munich, so maybe that's why you're confused there. Yeah, I'm Adrian, welcome. I'm, as already said, I work at the Science of Intelligence and the RBO lab at TU Berlin. And if you're interested in our research, check out our Twitter and or visit our website for more insights into the research we are doing. So in the end of the presentation, I will also say a few words about Science of Intelligence and what we are up to in this research cluster. But before, I will talk a little bit about my research, and it's about the interplay of the embodiment, the physical hardware, the natural dynamics that bodies have, and the consequences for the learning approaches, the priors that we can induce into the learning approaches to obtain dexterous, robotic, generalizable manipulation. So, and as often in robotics, we motivate what we do with human capabilities. So here's a chef acting in a restaurant in London, and as you can see, he performs multiple tasks and seamlessly switches between them. So he's operating tools, throwing sauce on the plate, so performing really fine manipulation. Then after he's done, he's placing the pot somewhere else, finds narrow space, navigates through the room by not hitting his colleagues. And this is somehow behavior that has not yet even been close replicated in a robotic system. I guess you all would agree there. And our hypothesis why this is the case is that we have not yet really figured out how we should design a learner, a brain, a controller, a policy, whatever you want to call it, that takes into account the physical properties of the embodiment of the hardware. Because in the end, this is what makes the robot act in the world, right? So how it can walk, how it can exert forces. It's about hardware interacting with hardware in the real world. So it's really dependent on the embodiment. And I mean, we humans evolved in a way that our brain is perfectly capable of using our tendons and muscles that result in the biomechanics such that we can efficiently traverse in the world. And somehow robotics has not yet embraced this decomposition. There was always the main. Hello, yeah, I'm back. There's always the main focus on developing controllers and the intelligent brain that lets robots that are only built to execute actions act in the world. So let's have this decomposition in mind. It will be the running theme throughout the talk. And let's ground what has happened on the AI side in this perspective. So those generative AI models like ChatGPT, DALL-E, OpenAI Jukebox, or also AlphaFold and AlphaGo, I guess you all have heard about them. They live in the digital world, so they can be considered as being a brain, only a brain. So they have no physical grounding. They don't act as a system in the real world, and that's why, yeah, they somehow are way further in terms of capabilities like our robotic agent. And this has also been already acknowledged at 1988 in Moravec's paradox. Maybe some of you have heard about that, so I will read it to you. It is comparatively easy to make computers or robots exhibit adult level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. And if you think about this gap has even widened with the recent advances in AI, and somehow the robotic systems have maybe slowly increased their performance, while the performance of an AI system went through the roof recently. But of course, people now are interested in how they can couple the brain, the large language models, to robotics. And there's recent work by Google. It's a paper, Do As I Can, Not As I Say. It has 60 authors on them, and they built this system here. So what this system can do is it accepts natural language input, and then the large language model that's behind is listing then a sequence of subtasks that then allows the robot to fulfill this task if every of those subtasks is executed successfully. And here the human user asks, I spilled my Coke on the table, how would you throw it away and bring me something to help clean? And then from a known set of skills, the robot, the large language model composes this plan, and then the robot tries to execute it. And in the end, it finds a sponge, brings it to the human, and will clean up the mess. Keep in mind that on the top left corner, it's 10x speed. So in real time, this is a pretty slow thing here. And also in the end, it hands over the sponge to the human, and the human cleans things up. So apparently it's hard to even get this skill reliably to work, because you need perception, you need to see where's the mess, you need to get in contact, and you need to rub it. So even though there have been 60 engineers on this paper, this skill somehow is not in the repertoire of the agent. And this is also, so to give you some more context how this system works, you start off from a predefined set of skills that are known to the agent. So the robot system that you have seen here is able to execute the skill, find an apple, find a Coke, find a sponge, pick up the apple, and so on. And then with prompt engineering, the large language model is constrained to output only plans that respect the skills available to the agent. And then the output is scored. So what is most likely being the output of the next token in that sense. So if you input, how would you put an apple on the table? I would then find an apple or pick up the apple or place the apple are the most likely outputs of the large language model. But then they, in addition, have for every skill, what I call an affordance function that somehow scores the appropriateness of the skill given the current sensory motor experience, like the image or the state of the robot. And when you see the image on the top right corner, then somehow tables are far away. That's why pick up the apple has a low score, because it's not possible to execute a skill because there is no apple nearby. That means find an apple gets a higher score, and then in the end, this skill is then picked to be added to the sequence, and that will be executed by the system. And then after this has been added, the prompt is extended and the whole thing is continued. And yeah, the main takeaway is here, you can use the physical grounding of the world in the large language model to somehow sequence skills only by natural language. And as soon as you have those skills, you can extend this list and with prompt engineering condition the large language model to use this in its repertoire. Yeah, but still, this is act somehow in robotics on a high level planning abstraction. But getting those skills, when you read, so when you dig into the paper, this is the most difficult thing, right? To get those skills reliably working on a robotic system. And this is also acknowledged by the main author of this paper. So in this tweet, it was asked, so what's left for robotics and reinforcement learning to do? I mean, if you see those videos, you can think about robotics as solved. You somehow say something to a system and it will fulfill this task. But he, in the end, also acknowledged the low-level skills. To obtain those skills are still the hardest part. And this is actually what robotics is all about, to get things, to act in the real world, to pick stuff up, to move around obstacles. And so, yeah, it's a nice application on the planning level, but not that much progress on the low-level skill manipulation capabilities level. And this is where my research comes into play, because I work with robotic hands and try to somehow learn or enrich them with the capabilities to robustly manipulate objects in hand, to robustly grasp stuff. And before I get into detail what I'm doing, I will give you an overview of the current learning paradigm in this regard with respect to dexterous manipulation. So when it's about dexterous manipulation in robotics and learning, all approaches somewhat converge to one paradigm. And learning is applied for two different aspects. First, for the policy, to obtain the controller. This happens most of the time, or it happens with deep reinforcement learning in simulation. And then domain randomization is used in the simulation where physical parameters of the system are varied, like the mass of an object, the friction of an object, and the initial placement of the object whatsoever. And then somehow this skill will then be encoded in a recurrent neural network that accepts as input the robot state, the object state, and then outputs the next action. And this domain randomization is used to have a zero-shot sim-to-real transfer. That means you learn a policy in simulation, and then you can directly deploy it on the real system, and it will somehow, hopefully, perform on par with the simulated twin. But in in-hand manipulation, we are considered with moving an object or controlling an object inside of the hand. So therefore, we need also some kind of object representation. So that means in those approaches, learning is also applied to perceive the object, to perceive the state of the object, or to represent the state of the object in a low-dimensional latent space that can then be used to be fed into the policy in order to make decisions. And what's happening is that multiple camera views are then regressed into the object pose in the hand. So what's the position, what's the orientation of the object that can then be used as input or in the reward function. And people always also investigated point cloud representation of those systems. So this is this learning paradigm for in-hand manipulation. And recently there have been lots of publications from multiple companies or research labs. And here are a few behaviors that have fallen out. And they already look pretty dexterous and versatile. So on the top left, this is work by OpenAI. You might have seen that where this shadow hand robot is able to manipulate a Rubik's Cube in one hand. That's actually also difficult for us to do with one hand. We normally use two hands for that, but somehow they trained the system to do this in one hand. On the top right, that was work where I was also involved in the early days from the German Aerospace Center, where they used their anthropomorphic hand and rotated the cube upside down. And on lower left is work by MIT, where they also trained the system to rotate now non-convex objects upside down, what is also the next step. And then there's work by Meta AI, where they did also some fine manipulation with the fingertips of a hand. Now, yeah, seeing those results, you might say, look, I mean, infinite manipulation could be solved if we get those capabilities. But those approaches come also with some limitations that I will talk about now. First, generalization. So this is the work by OpenAI, where they rotated this cube and learned the policy to do this. And in the top row, you see the performance of the learned policy in the real world. And this policy was able to visit 19 subsequent cube configurations of this cube without that the cube is falling out. But you can already see plus minus 70.1 means that it's a huge variance. So that's not like that you learn it and you are able to do it. It's like, okay, it works sometimes, but most of the time it falls out of the hand at the first try. And what they then did, they evaluated, okay, what does it take now to change the object and somehow get the system to work for this octagonal prism? And what they did, they used the pre-trained policy from the cube and in simulation retrained for this object and then deployed it on the real system. And you see the performance is now way worse, even if they have retrained the system. So, but when we think about a manipulation system that we want to deploy in our real-world agent that we want to have acting in the kitchen or in our household, we want to have some zero or one-shot learning, right? So we want to have the capabilities of the system generalize to similar objects or learn quickly adaptation to those similar-looking objects. And this paradigm with those hands is currently not capable of doing that. And I already shortly talked about this. The data required to get those systems to work is immense. So we are in the billions of data points needed to train those policies, and especially the work by OpenAI with the Rubik's Cube. It was estimated that they required 13,000 years of simulation time. And there was a Wired article where one person argued that the data needed for this policy in the end is the energy, the energy needed to get this system to be trained, or that the whole project needed, is 3 hours of a nuclear power plant. And I mean, this is somehow not scalable when we look into the future and how our systems somehow should learn. So now the question is why is it so difficult? And why do we need so much data, and why is generalization so limited? And now we come back to our decomposition. It's like that those approaches currently outsource all the complexity to the brain, to the policy. So all the uncertainty needs to be handled by the neural network that represents the policy, while the embodiment, those stiff hands, only move if a controller tells them to move. And therefore, whatever goes wrong, needs to be handled by the brain. And this is where my research now comes in. So we do not work on the algorithmic side mainly, but we somehow look at what happens now when we switch out the hardware and use hardware that is completely different to the hardware that is used in the works I just shown you. So this is the RBO Hand 3. It's the third version of our soft hands developed in our lab. They are built from soft deformable silicone. They are pneumatically actuated. And this hand is already pretty dexterous. It has 16 independent degrees of actuation that you can see marked in this on the slide here. So we can individually move all the fingers around. We can move the thumb around. We can even oppose the little finger with the thumb. So, and I brought one version here, so I will pass it around so you can have a look, touch it, and feel the softness of this hand. And so, why is it now useful to use such a hand? I would argue that this design incorporates a lot of the priors that we humans have in our hand. It's compliant, so that means we adapt to the shape of the environment or to an object without any control. So we simply get in contact and the hand deforms. So we don't need to control for that. That simply happens due to the natural dynamics, to the physics of those soft systems. Second, we have those soft pulps on the finger, and they create large contact patches such that we can get stable grasps, and slippage is, the danger of slippage is reduced. And third, this compliance reduces impacts or dampens impacts. That means the forces that are generated when we get into contact are lowered, and therefore the dynamics are smoothened in that sense, and that makes control of those easier.
Question?
Sure. Yeah, shoot.
Just wondering about once the hand touches its skin, variable pressure then too.
It can, yeah. So let's know what are the sensing capabilities of this hand, or what do you mean here? So we have pressure sensors for every of the air chambers, so we can see when something gets in contact, right? The volume compresses, the pressure increases, we can measure this. But we have also other sensor technologies for this hand to somehow feel what's going on when we interact with the world. I will talk about this later. Yeah, and to give you a little example how this hand can simplify control, I will show you a video here where, wait, here we are. So the hand holds here this wooden donut between the thumb and the index finger. And what we do now here is for 0.5 seconds, we will change the inflation of this thumb tip and this middle bellow. And everything that happens after those 0.5 seconds is purely a result of the physics playing out. And maybe you can pay attention to the movement of the index finger. So we do not actuate the index finger at all. This is purely a result of the system interacting with the object. So actuation started, we change the inflation. Now everything is done, but the system continues to rotate this sphere. And that means if you would like to implement such behavior on those rigid hands before, it would be a super difficult programming task in terms of the control, the balancing of the forces, and so on. And here it's just simply change the inflation by 10%, open loop, and then the behavior plays out. And maybe to give you an analogy that might help to think about what's happening here, you can compare those effects to a physical funnel. And what a funnel is doing, right, it takes granular material from a wide range of positions to a smaller region of the state space. And this happens by constraints. These are the funnel walls, and then the physics that play out when gravity and the granular material interacts with those funnel walls. And in our perspective, the constraints are provided by the hand, and through actuation, we can induce forces in order to let the physics do their job and help us manipulate the object. So, and this now motivates our first investigations that we did after we somehow designed this hand. We wanted to test it in the context of in-hand manipulation. So now we do the exact opposite as the reinforcement learning approaches. We want to outsource as much of the uncertainty handling to the hardware and keep the brain as simple as possible. So we use the soft hand, and we use open loop handcrafted actuation sequences to move the cube around in the hand.
Maybe you can clarify what open loop means.
Yeah, that's a good point. So open loop means we do not use any feedback, no visual feedback, no tactile feedback, to condition the actions that we are applying to the object or changes in the scene. So no matter what the object is, we always apply the same command. So that means everything. So if things are working out, then this is due to the hardware and not due to the actions that we are choosing, because we don't vary then. But you will see in soon what I mean by that. So how did we actually came up with those action sequences? We programmatically somehow mapped all the actuation, degrees of actuation of the hand, like the tip compartment or the base compartment of the index finger, to the sliders of those mixing board. And then we programmed the hand by moving those sliders around and found postures. And then we simply interpolated between those postures and obtained movement. Then we placed an object in there and see if we are able to rotate or to translate the cube in the hand. And it turned out that with policies that look like this, So a sequence of interpolation between postures of the hand, between keyframes. So policy is represented as a set of postures that we walk through. We are able to, all of this is open loop. To emphasize this again, we are able to come up with manipulation behavior that allows us to move a cube to any of its 24 configurations. And this is somehow a simple planner behind there that uses 6 motion primitives to move the cube around. And we are able to use gating, pivoting, controlled use of gravity. And I think motion-wise, if you compare this to the reinforcement learning approaches, it's somehow on par, but maybe even more fluent, right? If you see how the hand is moving. So that was surprising to us. And then we tested, okay, so what are now the generalization capabilities of the skills we have here? So then we tested, okay, we run the same action over and over again, and then we simply swap out the object that is in the hand that's in the hand. So here we run this what we call spin and shift skill. So we spin the object counterclockwise 90 degrees, and then we shift it back to its initial position. And things are working out for very different object of very different size with very different friction properties, while we are playing the exact same action over and over again. So here, generalization comes from the physics, from the way the hand is designed. And not only we can vary the objects, but the skills that we have can be sequenced nearly indefinitely. So here's a video where we spin and shift a cube 140 times without that it falls out of the hand. So that is somehow a behavior for inlet manipulation that has somehow not been seen before, that you can run those skills so often without things failing. You can even vary the execution speed because things are open loop. We simply need to scale the timing. So we somehow designed the skills when we set on the mixing board to run at maybe 12 seconds. And then we simply try it. So let's get it as fast as possible. And what you see here will be real time. And we are able to execute the spin and shift skill on this hand in less than a second. So we can even change the dynamics, right? The way things are accelerated by a lot, and things are still working out. And then we, run the same skill when everything takes a minute. And I will show you now the spin succeeding. So everything is now going slower. It has different dynamics, but still things are working out. Always the same action, no adaptations, only the time scaling here. So, and we tested further. So we varied the initial cube configuration when executing the skills, and then we placed it along the palm and executed those skills. And now went through a few of the configurations. And on the subsequent slide, I will show you trajectories of this cube when we track the motion of the cube in a motion capture system over time. It's very somehow analyzed how the position of the cube evolves when we execute those skills only once or in a looped manner when we are sequencing it. And these are the results. And especially the second row is interesting because we are somehow able to start from a wide distribution at the beginning, and somehow after executing this skill, we somehow compress where the object is only by means of action. And then those red lines are 20 looped executions. So that means as soon as we somehow converge with 1 or 2 trials into this red band over time, we do not leave it anymore. So we can then run the skill over and over again, and things are simply behaving nicely. And this now maybe, if you remember once or multiple slides before, here's this strong resemblance of a funnel, right? So this has exactly this funnel shape that we converge only by the means of simple actions and the physics playing out on this hand. Yeah, so to sum up, now we have 2 approaches to inlet manipulation: the learning heavy ones that require a lot of resources, and now the approach that we did with simple actions and the soft hand. So where's this discrepancy coming from? So, and we have one working hypothesis here is that saying we are given a manipulation task, and this green line over time is now the action trajectory that leads, the optimal action trajectory that leads to success of this task. And given the fact that we are able to design skills easily that can manipulate an object in hand, with soft hands, we somehow have a large margin, a large area between those orange trajectories where we can move in, and we always will succeed because the hardware will support us in fulfilling the task. And for those rigid hands that are used for the reinforcement learning approaches, somehow this band is way smaller. That means the controller has actually a harder time finding feasible actions because the actions that lead to success, or the area of the actions that lead to success in this space is way smaller. And due to that this band is smaller, the policy has a harder time ensuring that we stay within that. Otherwise, the object might slip, or we might generate too high forces that the object or the hand will break.
We have a question?
Yeah, sure.
Yes.
Yeah, but it seems like that would only apply to a system where you actually start from a physical equilibrium, and your end state is also like physical equilibrium, right? So if you think about walking, you can't really apply the same approach because you need to have closed loop system because you have you're not in equilibrium from the very beginning and through all the states, right? You need to balance the weight. And would you generalize this to those kind of tasks?
So also for walking, you can design systems where you use the passive dynamics of a system, right? So also we humans have those tendons and some springy behavior in our knees that support walking. And maybe then you also can derive policies that are not that simple, but that make use of those dynamics to somehow simplify the control, as if you would build a stiff robot where you would then somehow need to control every sub-movement. And there's also some interesting work that motivated also this approach to use the passive dynamics of a system that's called the passive dynamic walker. And this is a system that walks by itself if it somehow goes a slope downwards. So you need to kick it once at the beginning, and then the system walks until it reaches an endpoint or stopped or no slope is there anymore. So also in those approaches.
If you have 4 wheels, that would be easier, right?
That's right. Yeah. I designed a system for a task, right? Definitely.
I have another question. So, have you already tried using the same old deep learning algorithm on this more elastic hardware?
Yeah, I think that's an interesting idea. But there's one problem with those systems. So those rigid hands, they are designed such that you can easily model them, right? You understand the kinematics, so you know where things are after you change the position of a joint. And also the way it's designed, you can really reason about the frictional properties, that you assume you have point contacts whatsoever. But modeling those hands and simulating those hands is really difficult. So that's why we cannot go through simulation, collect lots of data, or train a policy in simulation, because we cannot simulate these hands accurately enough that we are somehow now constrained to the real world. I guess there are some abstractions in simulation that you could use, but we have not tried it yet. But this is mainly the reason that we cannot directly apply those approaches to this hand. Yeah. Okay, yeah. So having this hypothesis in mind that we can be more sloppy on the action side with soft hands, we come back to our decomposition. And of course, in the end, we do not want to hand design actions for every task we want the hand to perform, but we want also the brain contribution there to make the system even more robust and to enable learning of such skills in the first place. So we recently went into this and analyzed, okay, how should maybe the learning algorithms look like given the embodiment, giving the nice properties of the soft hand. So, and let's list those. So what is this perspective implying that we can then use on an algorithmic side? So we can have safer exploration. We can try out more random motions inside the hand without the risk of things slipping out of the hand because we already have most of the time a stable grasp. We can have a lower decision frequency because we can maybe make larger steps in the action space because with this large area of feasible actions, we might not run the risk of making a failure. That means, yeah, we can have lower frequency control, what also makes search easier. And the nice thing about soft hands is that they provide rich feedback. If you can somehow get feedback about a posture change of a finger, you can imagine if you grasp an object with such a hand and you exert external forces, or you change the inflation of one of the finger, you change the forces acting on the object, and this change will propagate through the whole system, that you can pick up this change on all the fingers that are involved because they will all move slightly if you perturb the object from the outside. So we have really, really rich tactile feedback in that sense. If the interaction changes, we can measure this if we have the right sensors. So in the end, we might want to have a system where we explore, make a large step towards our goal, explore again, and then continue doing that. Oh. But of course, as I said, we need feedback for this. We need sensing for this to learn anything, right? So what kind of feedback are we using? We measure the deformation of this hand because, as I said, compliant hands adapt to the shape of the object and they change also their shape when an object is moved or pushed inside the hand. Therefore, we can assume that if we can measure the deformation, we can also implicitly measure object state and object motion within the hand. So how do we measure deformation? So for the thumb joints that you have seen here on the hand, we attach flex sensors to measure the opening and closing of those. So here you can see an example where I manually deform the hand from the outside and I pick up the signal coming from the flex sensors. And you can see that quite proportional to the amount of deformation of this joint, I get feedback. And we also have sensorized versions of our fingers where we wrap the fingers around or wrap the fingers into a design or a layer of liquid metal that is filled into really, really tiny tubes. And if we then deform the finger, the tubes are compressed and the liquid metal changes its resistance that we can then detect in a change of the voltage. So here you can see if I now press the fingers to left or to right, I can get a response how it's deforming from those voltage changes of those liquid metal. So, and now, and the approach that we are now performing is, let's assume we can sense the deformation with those sensors, and we can somehow come up with a desired deformation that corresponds to a manipulation goal. How we will get this, I will come to later. But now the question is, how can we minimize this error to reach our desired state? And we use the simplest policy representation that you can imagine. We simply multiply the error with a matrix, so it's a linear mapping, scale everything by a scalar alpha, and then obtain a change of our actions that we then apply. And hopefully the error got reduced, and we apply this over and over again. So, and this J, it's called in robotics a Jacobian that relates action with change and deformation. So how does my action at every point in time, my inflation of the fingers, result in the deformation of the other fingers that are involved in a grasp? And this J is somehow our subject of learning because we cannot model it, because that would be analytically too complex. That means we need to gather data from the sensors that we have in order to represent that. Yeah. Mm-hmm.
So essentially what you are doing, so you are actually measuring the proprioceptory sensor system for the,
right.
for the things. Of course, there's another sensor system that humans use, And that's by vision.
Yeah,
So you can
good
measure
point.
now in the sense when you say that you cannot model it, actually when you do that, you model it.
Yeah.
By the way. So you can look at the results, but you actually measure the data and then you make a model out of the data. So in a sense, you are creating an implicit model for the system.
That's right. That's right. That's I mean, the Jacobian is always a local approximation
Yes, true.
to this complex nonlinear thingy.
Have you tried the vision part?
So not yet, but I think it can enrich that. So the thing why we went with this deformation first is that it's a really contact-centric representation. And from vision, you cannot extract somehow the forces acting or if a finger is in contact. But from the deformation, so if the deformation is 0, that means the finger is not in contact. But if it's unequal to 0, we somehow know things are in contact. And with soft fingers and continuums, you can also make assumptions about the proportionality. If things are deformed more, the forces acting on the systems are higher. But
Systems are pneumatic.
yeah, they are pneumatic. Yeah.
Yes, of course, you could measure.
Right. Yeah. You can measure the pressure as well. But the pressures, yeah, come with some challenges, but they can also simply be used here as one modality as well. Yeah. So, and now to show you how this now looks like. So coming back to this, to our hypothesis, saying we do explore, we estimate the Jacobian, we apply this Jacobian to make a change in the action, we estimate the Jacobian again, and then we apply this new Jacobian again. So here in this following video, I will now show you how this pipeline now works. So we inflate the finger to a predefined position, and then I grab the object and manually move it around in the hand. And then at the end of my motion, I capture at this point in time the deformation, and this will be my control goal. So I feed this difference between the deformed and undeformed state in sensor space into the system. And then I use the thumb and the little finger with those probing actions to estimate this Jacobian. And then I apply the Jacobian as long as I minimize the error. If not, I get a new Jacobian. So, and then I continue and error not minimized anymore, get a new Jacobian, change the direction of inflation to then reach our control goal. So I somehow needed to collect 3 data points here that I can use subsequently as somehow you can somehow interpret this as a learning phase. And this is now an inference phase where I simply reuse the Jacobians with a one nearest neighbor approach, where I simply get the current state of the system, look in my data set, what's the nearest Jacobian, and then I apply it again, and then I can recreate this motion with the Jacobians that I collected before. So I can somehow now in the real world, in the deformation space with this exploratory behavior, generate such skills within a minute. Yeah.
So it seems to move pretty far for every iteration of the,
right.
If you reapply the Jacobian.
Yeah.
And is there a reason for it? And what would happen if you tried to, every millimeter reapply?
Yeah, so I think that's now the benefit of the softness is that you don't need at every point in time the accurate Jacobian. A Jacobian that is good enough, that has, let's say, the right signs in its values. So if I do this gets larger, this gets smaller, is enough for this to behave reasonable, because somehow the error and the feedback somehow makes things work then. And that's only with the help of the softness, that we can be that sloppy and use this wide interval between those lines and make those huge non-optimal steps, but they are good enough to come close to the target. Yeah.
Am I correct that the Jacobian is actually different for every new object you manipulate?
I will come to this on the next slide. Yeah.
So you are also looking at the generalizability of your policies.
Right.
When that is happening. So one, if you would actually use the system in real world, it would actually contain a robotic kind of moving it upside down or having it sideways.
Yeah. I will also have videos for this.
So that's next slide.
Yeah, so what happens now if we change the environment, right? So let's say this is the optimal trajectory for one object, and now we change the object. It means now all of a sudden the optimal trajectory looks different. But for this as well, we have our sloppy interval for soft hands. That means we can now reach this target or to somehow move inside this space. We can now reuse one of the Jacobians we collected before, but we cannot reuse the second one. That means we need to explore and then add a new Jacobian to our systems in order to get it behaving also on the changed conditions. So, and maybe to sketch this algorithm out, how this looks like. So assume we had this this learning phase. So, and we have this still this funnel analogy. So we tile the funnel with those Jacobians. So, and then we change the object. We get the deformation of the system. We look up the closest Jacobian, Jacobian 2, we apply it, we reduce the error. Okay, nice. Now we look again for the closest Jacobian, Jacobian 3, we apply it. Okay, nice, it reduced the error. Now we take Jacobian 5, and all of a sudden we didn't reduce the error anymore. And then we kick in again this exploration phase. We get on the fly a new Jacobian with those probing motions. Then we refine the tiling of the funnel at this particular point in time. Then we apply Jacobian 6, go further down, and then we can reapply Jacobian 5, and now we reached our target. So this is a sketch of how this algorithm works, and it can be interpreted as online learning, right? When we see we have our local models are not good enough anymore, we get simply a new estimate in this area, and then we can enrich our data set or have a refined version of our funnel here. So, and now we tested this skill for different objects and also 7 for soft object. And how things look like now is that we start off with the 3 Jacobians that we collected for one object, and then we see, okay, does it generalize without a new Jacobian to new objects to reach the goal? And you can see for the Rubik's Cube and the cylinder, we don't need any new Jacobians, but for smaller objects or the softer objects, the dynamics somehow change locally, and the 3 Jacobians we have are not sufficient anymore. Then we get on the fly those new Jacobians, and then are still able to reach our control goals in those cases. So, and this online nature of the adaptation of those Jacobian can also be used to, if somehow we simulate actuator failure. So we collected the Jacobians with all of the 3 actuators, T1, T2, T3, TT movable, but now we disable combinations of those actuators and then apply the Jacobians. So that means some of the rows are not applicable anymore because we cannot change this. So we zero them out manually and say we cannot change this, the action of this actuator. And given the new circumstances, we can then query new Jacobians or new local models where only this subset is active. And how things are looking there, we again start from the 3 Jacobians that we collected for this one object, and then we somehow play out the system, and we can see that the system can adapt quickly by just getting the Jacobians that encode the effects of the available actuators, and then goes through the behavior. And here you can see in this case, the thumb tip and the last joint are disabled. That means it cannot, the most important parts to push over. So it then maximally inflated the remaining 2 ones to do its best to reach the target and to deform the ring finger to the right. And kinematically, it's simply not further possible, but it tried as good as it can to do that. So, and the last generalization study we ran is like, okay, so now we turn the hand 360 degrees and run the same skill over and over again and see, okay, will the object fall out of the hand, or what will happen? And here you can see that for steps of 90 degrees, things also behave nicely, and the system adapts to the to the change of gravity. So here the system needs to act against gravity. So it needs to inflate more, it needs to exert more forces downwards, while on the right side, gravity already helps to reach the control goal, and only a few actuations are required to reach the target. Okay, yeah, let's conclude. So this is our somehow preliminary work on the learning side, and to thinking about algorithms that build on top of the useful properties of the embodiment of the physical system in interacting with the world, and we embed then those priors that we learned about into somehow an algorithm to efficiently learn in the real world and to have quick generalization capabilities. And now we look into maybe how can we autonomously discover skills in the space of all possible hand-object configurations, that we maybe have a mechanism where we learn about the possibilities to change the deformation within a given hand-object state, and then we maybe remove a finger, add a finger, and then learn about how we can modulate deformation in this new somehow contact object setup. And by doing this in an autonomous fashion, we also at the same time learn how those things belong together and how they can be sequenced. And then we can somehow sequence such skills in order to compose long, more complicated manipulation sequences. The second thing that we are researching also in the lab that other PhDs are interested in is co-designing the brain and the embodiment at the same time. So you can imagine that for certain tasks, you need those stiff, precise hands, while for other tasks, it's good enough if you have maybe a really simple, soft hand if you only want to grasp one particular type of object. And then this co-design approach would somehow scale the influence of those dimensions automatically in order to then spit out an appropriate embodiment with an appropriate control sequence or an appropriate feedback controller for the particular task that you want to perform. Okay, yeah, and maybe at some point we can enrich this system that I showed you before with dexterous hands that then have the skills that you can then prompt the system like, please prepare me lasagna for lunch, and then goes to the kitchen and performs everything you need. And at the time you can do other things, sitting on the couch and relax and look at the robotic system unroll. Yeah, I want to thank the collaborators on the research I did here. It's Aditya, Steffen, Vincent, and of course, Professor Oliver Brock. And before I close, I want to say a few words, as I said at the beginning, science of intelligence. So science of intelligence is an excellence cluster funded by the DFG, where all of the Berlin universities involved and researchers from multiple disciplines work together, like biologists, neuroscientists, philosophers, on the somehow more analytic side of things. And on the synthetic side, we have machine learning researchers, control theory researchers, of course, roboticists, and so that we can shed light on intelligence from the artificial as from the natural perspective, and then hope to use insights we gain on the natural side, that maybe biologists investigate the behavior of humans or of animals, and then we hope to learn from the data they collect and embed the principles of their behavior into artificial agents that we can then use and test on different scenarios. And the hypothesis is that an artificial system you can run, if you like, 24/7. You can change the internal parameters and you can then probe the system along the parameters you identified might be reasonable. And the hope is then that then you can loop back to the biologists interesting questions such that they can adapt their experiments in order to get even more of a deeper insight. And hopefully by going through this over and over, we will understand how natural intelligence, how agents, animals, humans act in the world and perform the tasks that they need to. And maybe 2 examples of animals that are studied that might not be perfectly obvious that they can do that. So this is a kakadu opening a physical lockbox where it needs to unscrew nuts, where it needs to open door mechanisms to, in the end, reach something to eat. And interestingly, those birds can learn opening such actually difficult mechanical puzzle because they don't have a hand, they only have their beak in reasonable amounts of steps. So, and it's interesting how they maybe explore, how they do approach the problem, how do they solve that efficiently. And another system that is studied are mice, and also how mice open such lock boxes in order to retrieve some food in the end. And also what you see also in mice is that they can learn this also pretty efficiently, but then in the meantime, they have some playtime, they walk around, but at some point they come back and open subsequently all the steps that are required. So maybe they need to think about what to do next while running around and then coming back and being able to then remove all the obstacles in the way to get their food. Now opening the last door and then it found its reward. Yeah, so that's all from my side. Thank you for your attention, and now we can have a few more questions.
Thank you.
Check. Yeah, thank you very much. Really like the topic and the approach, super practical. Even though there is no AI, but it works. The question is, so if we think about real applications, not like rotating Rubik's Cube, but if you need to actually like pick something, so it means that your goal state is not in the geometrical configuration space, but it's in force space. So you don't care about like how fingers are placed until there is enough friction, right? Mm-hmm. So, and how would you transform that into like force space, really targeting like, I just need to apply enough forces in those directions to this object. So, and how do you use like the same approach for this?
So that, I mean, also depends on the task. If you're only interested in grasping an object, you might not need to go through the hassle of going into force space in the first place. If you have maybe the right primitives that you simply close a hand and then the force is appropriate for a certain set of objects emerge. So I can also show you a video where we applied the hand to grasping and to analyze in the end. So we looked also at how humans grasp. So we have an anthropomorphic hand, and humans use a lot of the environment to pick up stuff. And then we try to replicate this with the soft hand. And we also, again, here run the same open loop synergy over and over again. And we simply change the object there, and the hand is able to pick up those different geometries. But of course, maybe for some objects you want to be, you need to apply a certain force, otherwise you will break the object. Then of course you maybe can also go into the deformation space and maybe learn a mapping about, okay, what deformation maybe corresponds to which force in order to do that. And one approach that we are using is, so you have seen those strain sensors. We have a second sensor technology that's called acoustic sensing, where we have a microphone and a speaker inside the finger, and we somehow measure how the sound is modulated when we change the interaction with the finger. If we apply more force, if we touch the finger at different points, and then you can collect ground truth data, right? So you can mount the finger crosstalk sensor, then you can deform the finger, record the signals, then you can learn a mapping between the raw data, the acoustic signal, or the voltage of the strain signals, and map this into the force space. And then you can use this data to reason about what forces are acting at which point. Of course, you need to collect the data first, and you need to know what's your task, but that might be one approach. Yeah.
Yeah, I think like, can I have like second one? Yeah. Second one is, do you do any kind of technology transfer for this? Like, because I can imagine like many companies, maybe including myself, would be happy to buy this actuator. So do you have any development on this side?
I mean, so the whole design of the hand is open source on our website. So you can download the files, you can 3D print your parts. You need some silicone to mold things. Yeah, so building this hand is actually comparatively easy. What's the more tricky part, I guess, and the more costly part is the valve system that you need to use in order to control the system. We also have this open source on our website, but yeah, so here you can see how the whole system looked like. So we always see the hand, but of course, that might also be a reason why it might be difficult to apply this in a real scenario is that we need a compressor, right? Of course, there are miniature compressors. We can miniaturize this. If we focus on doing that, then we have here our valve banks that can also, I guess, be optimized in shape. But maybe to bring all of this into a forearm requires some heavy engineering to be done. So that's why I guess such a system is not yet ready to be rolled out yet. But maybe if a company decides to investigate this and then to optimize those engineering challenges, it might be. Yeah.
I also have a question. So we talked a lot about, thank you so much for the talk. First of all, it's been very fascinating, very, very good to follow and super interesting. So we talked a lot about the embodiment of the hand and the brain that connects to the hand. However, there was this third component, the world. And I was wondering like how the world and its embodiment can be integrated into these new types of control approaches.
Yeah, so that's an interesting question. And as you have seen with those examples, how human grasp stuff, they use interactions with the world heavily, right? They move their hand to the table and then close the object, close around the object to grasp it. So also using the environment simplifies the control that you need to do in order to perform a task. And then you can think about an approach. Maybe you have a task, you want to pick something up, and you can then co-design hand, brain, and maybe environment, right? That you place walls, that you change the slope of certain things in order to optimize for having a simple policy and a simple behavior, performing the desired task. So co-designing the environment is definitely something that that can be done as well. And I mean, if you think about the current systems in industry, you over-engineer the environment such that the system, the robot system, can easily interact with the environment because it knows perfectly where everything is. Yeah.
Thank you.
Oh, yeah, yes, thanks for a great talk. I had 3 questions on which I'm on top of. So one of the things is about the Jacobians and how they perform if you start using slippery objects. So that is something that OpenAI kind of in the Doctoral uses this kind of a super kind of reality to simulate everything in beforehand, so they can handle that. So this is the second one is about energy consumption of these different options that you have when you split the Jacobian. So which are the movements that are actually good for energy and which are the ones that consume more? Because this is very essential on the system. It's also about latency on the actions that you do in that affects on the third part is more about this question about what happens if you take some fingers off. And then the question is that how do you now claim that this five finger thinking is the optimal evolutionary goal that actually does things better than everything else? So
yeah,
okay.
Okay, so I will start with the last question. Why the anthropomorphic design? I mean, we started off with the hand. So my professor always tells the story. The first version of the RBO hand didn't look anthropomorphic, and still back then with this simple hand that didn't have a thumb, it only had 4 fingers and a palm. It has been able to grasp a lot of stuff, but somehow the community wasn't impressed because it didn't look anthropomorphic. So they built a hand that looked anthropomorphic, and that won Best Paper Award at one of the top conferences. So I mean, you can sell anthropomorphic design simply better. but still design-wise. So designing a hand that replicates what we are having is easier for us because we know what's required. We can look at ourselves, what are the range of motion. Also from the biomechanic perspective, there are a lot of papers about force generation in the hand, movements of the hand. So you can open an anatomy book and then look at, okay, how are the tendons routed and whatsoever, and you can understand a lot. So building anthropomorphic hands is simpler than starting with a maybe more optimal design, but it's not so intuitive to build that. And of course, I mean, you can study humans and it's a general purpose tool. We want to have a general purpose manipulator in the long run. The first question with respect to the slippery object, of course, that is always a problem. That these are then the trajectories where we would cross this orange line that I always showed. And one thing that we tried out is when you can use the Jacobian for control, but you can also use the Jacobian vice versa to make predictions. So we use the transpose of the Jacobian for control, and you can use the Jacobian to predict what, if you apply those actions, how should the system evolve? And in SLAP, what happens when you slip, that means one finger moves out of contact in an undesired direction. So you can track the prediction error and see when in the prediction error you have a large value or sign changes, then you can intervene and locally adopt the Jacobian to revert this motion. But that is one idea where we run some little experiments yet, but not a completely boiled out algorithm or theory. Maybe that might be an approach. And could you rephrase the second question, please? Yeah.
Second question is in a way related to number 3. So it's about this: what are the actions that are the most energy efficient and produce the low latency and produce the low latency kind of, let's say, solution for those things? Because I think that why is my asking about that is that, for example, when Amazon is trying to make the picking robot exactly for the warehouses,
yeah,
humans are still better.
Right.
And now the question is that how do you actually solve that problem? And it would actually be on those topics that solve the problem for them. So.
So we have not looked at that yet, but somehow alone doing manipulation with a hand is, I guess, more energy efficient if you do it with a gripper and large arm movements. So the little local nature of our finger movements are already energy efficient, I would argue. And if you have such a hand, you maybe need less arm movements in a system to, yeah. So we haven't measured that, yeah. So, yeah. Yeah, that's right, yeah. But it wasn't of interest yet in the approach, yeah.
Any other questions?
So I've heard that there's excitement about applying transformers, which obviously, completely change language models to mechanics. And I wonder, like, if you have any thoughts on that, if you think it's promising, or how do you feel about that?
So in the robotics context or the transformers
in the context of robotics, I believe it's like, you look at how some motion happens and you sort of try to predict future motion instead of future language.
So there's definitely interesting and recent work going on by a Berkeley lab, Sergey Levin. Maybe you have heard of this researcher. He just recently published a paper where you collect a lot of demonstrations, and then from those successful demonstrations, you can also train a transformer architecture to use this as a policy. So these are really, really recent works, and one needs to see if they stand the test of time and if this will actually be an ingredient. But so my impression is that you can solve problems oftentimes way simpler without using the sledgehammer of transformers and heavy learning. For example, this SEICAN that I showed you at the beginning, that I also did reinforcement learning to pick the object. And when you read the paper, they collected 68,000 successful demonstrations over 11 months. So they, I guess, hired a fleet of research engineers to collect data simply to pick up stuff, right? And in robotics, you have algorithms, it's called visual servoing, and then you can somehow do simple feedback control, I guess, where you can also get far solving those problems and maybe even more generalizable without using learning for this. So I think it's important to figure out, do you need learning and where do you need learning, and can you actually get the data to do that? But I mean, it showed success on the language model side. It seems to show success on the robotics side in recent papers. So maybe in 1 year, we can evaluate this better, how useful it will be. Yeah.
I also have one more question. So you just touched upon visual servoing, which is essentially trying to control the robot by using imagery of what's going on.
Yeah.
So I think the examples that you showed were mostly based on state space that is generated from like the angular deflection of the hand, right? And the individual fingers.
Right.
What potential and drawbacks do you see in using vision for controlling the hand, or like as a feedback signal for controlling the hand?
So I think we need for such system both things, right? So if we somehow place an object simply on the hand, we don't have yet any deformation or tactile feedback. Maybe we need to place it on the palm, and then vision is interesting to see, okay, how can we approach it and how can we use it? And of course, vision is also interesting because it gives us global information. And if we have a super good object position tracker, then this is super valuable feedback to somehow confirm that the object move as it should move, because in this tactile proprioception space, things are implicit. So we cannot say, as of now, move 2 centimeters to the right. But maybe coupling a vision system to this, we can control the deformation while tracking of how far things are going, and then stop if some of things moved enough, right? I think those 2 sensory modalities can nicely complement each other.
Any more questions? Then I have a final one. Sorry. So the lab that I used to work in, they basically focused on building very precise tactile sensors to control robotic hands, and like to build very accurate models of the world to control these hands. However, like now it seems you don't really need such an accurate model of the world. Like the world will somehow eventually develop in a predictable way anyway. So you present this idea on this energetic funnel.
Yeah.
Is there any advantage of having like super precise tactile sensors in this hand? So what would you do with like data that would be a sub-millimeter precision tactile feedback? Like, would that be of any use to this hand?
Yeah, so I think one really interesting use case for this is estimating object properties of an object you have in the hand. So we can now move objects around, but it would also be nice while you're manipulating, you build a representation of the object that you are manipulating. And there's also research on the human, and the human has a 5 to 6 exploratory movements like enclosing, edge following, and whatsoever. And there you can, I guess, develop really nice algorithms where you have this precise local data where you can really detect edges, for example, to incrementally build a map of the objects you have in hand, to then in the end more efficiently manipulated. Yeah. So,
makes sense. Thanks.
Yeah.
Cool. If there are no further questions, then I'd like to thank our speaker once again.
Yeah, thank you very much.
Yeah, it's really been a fascinating talk, and a pleasure to have you around. And yeah, please stick around and use this space as also like a connection space to talk to each other a little bit. And yeah, I'm very happy to host you. There are a few drinks left and snacks, so feel free to grab those, and I'll look forward to seeing you next time. Thanks.